Today, I wish to draw your attention to the other side of the whole AI revolution. Some might even refer to this as the less glamorous side, right? I'm just going to put that out there. So I'm going to be talking about optimizing network storage for AI-powered EDA workflows. As design teams frantically explore and move towards AI-powered flows, there are some things that are happening behind the scenes, quietly, that increase the impact on network storage, right? So firstly, these workflows not only generate a lot of files, but they also access large data sets with lots of small files. When such large data sets have to be replicated or distributed among large teams that are spread out over different geographies, scalability, performance, and cost take a big hit. Now, AI promises big, but it also drastically increases the strain on network storage. What we really need is an effective way to reduce the storage needs to handle the explosion of data that is due to AI-enabled EDA workflows, right? So to understand the impact of lots of small files on network storage, here's an example of how much data and what kind of data is typically mounted on NFS drives, because everyone needs to access these tools and project work areas, common areas like the PDK libraries that are probably stored somewhere else, and then IPs and other scratch areas that are used by designers, and also a caching area, right? So these are some examples. And all of this is potential training data for AI MLOps flows, right? And larger the footprint of this training data, it's going to take you a lot more processing time to get through whatever workflow it is that you're doing, right? So typically SOC projects have about somewhere from 100,000 to 5 million small to medium files, each ranging from like 1 kilobyte to about tens of gigabytes, right? Now, the solution that I'm going to show you today is a smart caching agent that keeps track of who is using what and from where, right? It finds actively used data and automatically deduplicates them across different user work areas, and also cleans itself up by scrubbing versions that are no longer used in any of the projects, right? So let's take this example. So I'm going to use this slide to explain the caching agent solution to you. So an example of a library A that has, cells A1 and A2, and then it has layouts and schematics and a whole bunch of other views. And each of these have leaf level cells like the layout.oa, master.tag. It could have a bunch of other files, right? So in a typical traditional a data management system, or if you look at a work area, user work area is going to have physical files sitting there, right? So that's the example of that. And when you take our solution, which uses a smart caching agent, you'll see that the leaf level files under layout and schematic, they're actually symbolic links pointing to the cache. So all these files have now been replaced with symbolic links, right? And I'll talk about the benefits just in a moment. And here is the other mode that we have, where you could have a sparsely populated directory, which is just one link pointing at the very top level of library A. It's just a link pointing directly to the cache. So the user work areas, think about it. How much space are we saving in all these user work areas by not unnecessarily replicating all the data physically on there, right? So the benefits of this, right? So if you look at the traditional physical copies, you'll see that the leaf level files are physical copies. There are no symbolic links. You get to the fully populated directory, you'll see leaf level files being links to physical copies. And right there, what you will see is that there is one order of magnitude storage savings that you have achieved. But you get to the next level, you see the sparsely populated directory is just one symbolic link. So of course, you're saving a whole bunch of space there. And the benefits are obvious. The the setup time and the design bring up time is almost instantaneous, and there's just a lot less data that you have to deal with overall, and not to mention significant savings on the inodes. So here are my results of my what I've done with this one AFE example library. You'll see the three different modes, right? The first one is a traditional physical copies work area, which most other data management tools provides us the only solution. What Keysight Design Data Management SOS provides is the fully populated links to cache work areas and the sparsely populated work areas. You'll see for the same AFE library that has 5,000 files in it at the leaf level, that's about 2.8 gigabytes. And then moving on to the next stage, it's reducing to just about 75 megabytes, and it's because of all the symbolic links in there instead of the files. And you'll see all of those files are now links. And in this last diagram here, you can see that it's only 4 kilobytes because it's really just one link. Here, you'll be able to see what's under it. You see an ADC logic, you see AFE top, you see all of these layout views, schematic view, and everything. But here, you only see AFE. So you know that this is linking, it's a sparsely populated directory. We do have tooltips that will tell you that this is a library that is pointing to, it's sparsely populated and it's pointing to the cache. It'll give you the path and the cache in case you're interested. But here, you won't know the difference at all. It's just on the disk that it's a link versus a physical copy. Your tool, if you're using Cadence Virtuoso or Synopsys Custom Compiler, has no idea. It doesn't care. The underlying data, it's there, right? Whether it's a link or a physical copy. So I have two real-world customer examples to show you, and this is the first one. So we have a large FPGA system design team, and they were working on this mixed signal design project with 44 IPs from 4 vendors, including OA libraries, soft IPs, hard IPs, verification IPs, right? So what they had or have, this is a pretty recent example actually. So they have a total number of work areas for this project to be 120. And the size of each work area in their case was about 185 gigabytes. Now, if you take a local copies work area, which is, again, the only mode that is supported by other data management systems, you'll see, you can do the math and just, time it, and it's going to be 22 terabytes, right? Now you switch to a links to cache type of work area, and almost all our customers use this. This is one of our most popular features, actually. If you do the math, now the individual work area size gets down to 57 megabytes times 120 work areas, but you have to account for the actual caches that are there in each of the remote locations, right? So they had 3 geographical sites, and each site has a cache. So it's plus 3 times 185 gigabytes of, cache data in there, which comes up to about 600 gigabytes, and that's a 97.3% saving there, right? So that is huge, and we have one more customer example here. This is a mid-size automotive semiconductor design team. It's actually one of our customers in Europe, and this is across across this particular team, design team. They have at any point of time working on 10 projects, and total number of work areas 20 per project, and they have about 5 variants of these projects, right? And this is the work area size without any cache, so that would be the local copies, traditional type of work area, which is about 3.2 gigabytes in their case. And if they were cached, the work area size comes down to 87 megabytes, right? That's, again, an order of magnitude less. So if you, I'm going to show you the difference when you calculate it across the 10 projects, across all their variants. You'll see the work area size that needs to be provisioned is 3.2 terabytes. And in the links to cache type of work area, it's about 90 gigabytes, right? That's including the cache size that they have. So it's, again, a 97.2% saving. That's a whole lot. So anyway, so with those two examples, to conclude, the strain on network storage from these AI-powered EDA workflows is very real. That's what I want to emphasize on, because it generates a lot of small files. Everything you see in there, all the design data, they are potentially training data for these AI models. And if you can reduce the network storage size, it's a huge plus. So the need to distribute all this data across hundreds of thousands of users in different parts of the world will only exponentially increase the strain on the network storage. So as we saw in the real world examples today, smart caching agents with automatic deduplication of frequently used data right from the get-go will alleviate this strain by reducing an average of about 90% storage needs, right? And provide much better performance and scalable growth in the AI EDA integration space.